So today we will see the second part of the Warshall's algorithm. So on the kth iteration, what it says is that on the kth iteration, the algorithm determine if a path exists. If a path exists between two vertices, suppose I got one vertex is that is I and J, these are the two vertices. So if the path exists between this, either this or either this, using but just vertices among 1 to dash k allowed in as intermediate. So on the kth iterations, the algorithm determine if a path exists between the two vertices, whether there is a path exists between the two points are there, using the vertices among the 1 to k allowed as intermediates. So in between this, there should be 1 to k vertices are there. So in between this, there are many vertices. So if there are many vertices, then that will be called as a path from I to j. So this is so simple. So I to j. So there are the vertices are there. So many vertices are there. Maybe 2, 3, 4, 5 vertices are there. So these vertices may be going from I to j. Okay. So that can be written as, we can see that the capital R is there. Okay. So we got the K is, and then I got the I comma J. Okay. So capital R. So K minus 1 will be there. So I comma J. So again you can see that R raised to K minus 1. Okay. And it may be the of I. So I must say that I got the, you can see by the diagram. So I to the J, if there is a path, okay, I to the J there is a path. So this path may be like this. So I got a many nodes in this K, and then I can connect this to this one. So there are in between the so many K's are there. So I should say that to the first part of this equation, what I should say, path just using 1 to k minus 1 for this. The path is, we are using it, will only be just 1 to k minus 1. Okay. And for this now, for this second one, for second alternative, so the path is from I to k and k to I again. So k to I using just I to k minus 1. So the path from I to k and k to j is also there. So from this is nothing but the this is going to be the including the path from I to k and then k to I. That is, this is I to k and k to I. This is for this one. Okay. So I to k and k to j using k minus 1 various paths which are available. So we must say that the all this is comes under the kth iterations. So you can use it a kth iterations. Okay. So this is what we see in the second step. That is, on the kth iteration, the algorithm determines, the second step determines if a path exists between the two vertices. If the path exists between the two vertices using just vertices among the 1 to k allowed as an intermediate. So intermediate vertices are allowed in between to I to j. So that is the second step. This is called as a second step. Okay. So we will go to the next part of it. So transitive closure of the graph, where we will see the transitive closure. In the transitive closure, we have got a A, we have got a B, we have got C, we have got a D now. Okay, so the graph is there, and then another graph is there. This is so just like we have seen it already in the first part, that we have got this matrix A, B, C, D is there. Again, A, B, C, and D is there. So let us have the matrix. So A to B is there. So A to B is 1. And is it there any path? No path is there. 0, 0, 0. And 0, 0, 0, 1, because 0, 0, 0, 1 is there, because there is a path from B to B. So B to B is there. B to B, there is directional path is there. B to B. So this is directed graph. Okay. So C is having a 0, 0, 0, 0, and then D will be the 1, 0, 1, 0. So this is the first matrix. Okay. This is the first matrix. We will go to the transpose matrix. How can you calculate the transpose matrix? Which we have already seen in that with the help of the last the theorem. That is, if there is anything between the two vertices, then we have to accept that these are the vertices between the two nodes. Now, let us see now the transpose vertices A, B, C, D. A, B, and C, D is there. So the vertices is there in between A and A is there. Vertex, yes. And I can transit myself to the A. So there is 1. And there is a B path. Yes, A to B, there is a path 1. Okay. Yes, there is path from A to C. Yes, A to B, B to B, D to C. So there is a path. Is it there is a path to B? Yes, A to B, B to D. So 1 is there. So in this way, I got again B to A. There is a path to the B to A. Yes, I can go to the B to D, then D to A. That's why it is a 1. There is a path of B to B itself. There is a path to B to A. I can go there also. And B to C. B to C means B to D, D to C. So 1. In this way, I can put it there. The C cannot go because there is no direction at all towards the any vertices other than the C now. So you can see now there is no other vertices. There is no edge which is going from the C. So the only one is coming in. There is no out edge is there. That's why we can say that C is a 0, 0, 0, and 0. And 1, 1, 1, 1, 1, 1. Because you can say the D can be achieved from A to B to D, then D can be achieved D, and also the D can be achieved by the C also. How can I say? I can write go to A, B, and then again D to C, or D to C also. So D to D is already there. So this is actually a transpose matrix. So the or you can say the transitive matrix also. This is also called as transitive matrix. So this is the second part of the our Warshall's algorithm. And if you go to the Warshall's algorithm, we have done it. The reference relating to the element R of k to elements R of k minus a is, so recurrence is there. So recurrence relations elements is there. So we have got a recurrence element. These elements are called as elements which are in the matrix are called as recurrent elements. That is R of k, you can say, to the elements R of k plus 1 is the recurrent elements. So I must say that recurrent elements R of k, arrow k, you can say like this, arrow k of ij is equal to recurrence element of that matrix of k minus 1 will become I comma j. Or we can say that or we can also say that the r k minus 1, and then we can say that there is I k and k minus 1, that is the recurrence element. So r k minus 1, then I got the k of j. So I will go from I to k to k. There is already there is common vertices, and then k to j. So this is what is the recurrent elements. It implies that the following rules. What rules is there in the second part of the Warshall algorithm is that if an element is a row, the first rule, which is rule, first rule is that if an element in a row is I and column is j, column j is 1 from, that is in the recurrent of that what we said in previous part. So k minus 1, okay, recurrence in k minus 1 matrices. So it remains or it retains 1 in the R again. So it remains or it retains 1 to R of k also. So if an element row I column j is 1, so in Rk minus 1 in the previous matrix of recurrence, if it is 1, then it retains 1 to the Rk in the next matrix. In the first matrix, the next matrix, the previous matrix, if it is 1, some of the element is 1, so same element will be the 1 also in the next matrix, in this way. So until it ends, so it remains 1. This is the first rule. Okay. So what is the second rule? Rule number second is that if an element row I and column j, if row I and column j is 0, if it is 0, in Rk minus, that is if it is in the Rk minus 1 iterations matrix, okay, so it has to be changed to 1, it has to be changed, it has to be changed to 1. How? In R of k, that is in the next matrix. Only if and only if the element its row I column k, if elements in its row of I and k and the elements in the row in the column j and row k are both 1, okay, both are the 1. So in a Rk minus 1. Okay. So so if an element in a row I, and column j is 0, then what will happen? If an element in a row I and j is 0, in Rk minus 1, it has to be changed to 1 in recurring matrix K if and only if the elements in its row I, column K, and the element in its row J and K are both ones in a Rk minus 1. That is in a previous matrix. If it is in a previous matrix. The previous matrix, I got the Ik and Jk is equal to 1. Then I can change it to the 1 in a K minus 1. So this is very important that if I want to change it to the Rk minus 1, if it is 0, if I want to make it 0, so I can take it Ik and Jk. You can see also the Ik and Jk, both the vertices are there. So both the vertices, if I put it the 1, if there is a path between I and K and J and K, then I can put it 1, then both the 1 will go to be the path between the I and J. So there will be the path between I and J. That's why it comes out to be a 1. Okay. So the rule of zeros in Warshall's algorithm, the rules of the zeros in Warshall's algorithm is like this. The transitive closure. So I must say that R K minus 1 is the matrix where K is the kth is the element. So we can say now if this is a column, okay, which is a kth column is there, okay, then it is a j column is there, and also I got also this is another one, row is there, kth row is there. So I got this is one, so I got a k and I is there. So meaning is that if I got 1 here, okay, and if I got a 0 here, the meaning is that if I got a j to I is a 0, that is j to I is a 0, then if I put it here as 1, if I put it I to k to I is 1, then what will be done is that, very important, then R of k, the next matrix will be, that is in the kth row and ith column. In kth column, I must say that I will write it here, it is as 1, and I should say that if it is I is there, I must say that this is also 1. So I will make it all these three. 1 means I will make it this as a 1. So we can say that 0 to 1. So this is called as rule of changing zeros. This is called as a rule of changing zero in Warshall's algorithm. Which in the Warshall's algorithm. Okay. So you can see now the rule of change of Warshall's algorithm. That is so this is called as a Warshall algorithm, second part. Okay. Now we see the application of Warshall algorithm to the diagram shown. We see the example for this. Again, we'll go for the example. That is, this is A, this is B, this is C, this is D. So there is the path. Once again, I will write it small so that you can get it down. So write it down here. So again, I will write it the R. So I will write it first R0. So the recurrence number 0 matrix. What will be this? This matrix will be first matrix. So I got a B, C, and D is there. So I got a B, and C, and D is there. Okay. So what I should do is that A to A. So I will put it this as 0. Okay. The 0th recurrence. I will go to the A to B. So I will have a A to B. So 1 is there. Okay. And I also got the in the first recurrence, I got a B to C. So I will put it this B to C, A to B, B to C, B2 D, sorry, B2D. B2D. This is B2D. So I'll put it 0, 0, 0, 0, 0. Next one C is not there, so 0, 0. As it is, which we have seen it in the last one. So 1, 0, 1, 0. Okay, this is the recurrence number. First, what is the recurrence number 1? Again, I will put it, I don't want to write it ABCD here. No? ABCD is there in the 4 by 4 column, 4 by 4 matrix. What will happen is that, so I got now these, the recurrent, I will put it this as now, I will change this now in this way. So I will put it this as a 1 instead of 0. So what will happen is that, so I got you can see now here, this is 1 and this one is also there. Okay, so so D, so what I have to do is that, so I got you can see now here, what is the common is here now. So I will put it now. So I got D is there. So B to D, okay, B to D is there, okay, and B to 1, B to A is also there, B to A is also there. So I got AD, that is also as I and J, okay? And then I can also say that this is I and J. That's why I can put it here. Once they reflect the existence of the paths with intermediate vertices numbered not higher than this, that is just vertex, note that the new path from B to B is there. So B to B is new path. So B to B is with the B to B is a new path. So the box to the row column and are used. So you can say now here the new path I will get it. So the new path I will get it. That is also called as 1. So new path is I will take it. So the B to B is a new path. Okay. So B to B is a new path. B to A to B. So this is one of the intermediate variable. Okay. So I will make it like this in this way. So I will make it the recurrence and recurrence and recurrence in this way. So I will make the last part. So I will make it like this, and then you will see that I will get the last one in the recurrence 4. So whenever there is a path between the vertices through the any vertices, I am saying the any vertices, if there is a path between two vertices through the any vertices, then I will put it 1. So I will put it 1, 1, 1, 1, okay, and 1, 1, 1, 1, and there is no path between 0, 0, 0. What we have seen in the previous lecture, the same thing will happen. So we will get it this matrix directly. So instead of doing all these things, you can directly put it, if there is a path between the one vertex, two vertices to the other vertices, then we will put the 1. That's all. So we write it pseudocode for this. Pseudocode for the Warshall's algorithm. What is the pseudocode for the Warshall algorithm is that? So this is algorithm. What is algorithm? Warshall's algorithm. Where capital A is your matrix 1 to n, comma 1 to n is a matrix. Implements Warshall algorithm for computing the transitive closure. Input is the adjacency matrix A of a diagram with the n vertices. Input is, what is the input? Input is the adjacency matrix. So adjacency matrix A, okay, of a diagram with the n vertices. With the n vertices. This is input. What will the output? Output will be the transitive closure of a diagram. Transitive closure of a diagram. This is going to be the algorithm of our Warshall algorithms. So in the recurring, so I will put it the 0th recurring, that is the matrix. As it I will go to the first, I will take it as it is the matrix to the recurring number first, that is recurring number first matrix. For K is equal to, I will write it now on the upper part so that you can understand. This is input and output we have written already. So I will start with a 0 recurring. Okay, I will put this as matrix A as it is for K is equal to 1 to n do. Okay, and for I is equal to 1 to n do. For J is equal to 1 to m do. Same thing what we have seen it in the previous one, that is R of K of Ij going to be the R of K minus 1 Ij. Okay, or we can say that R K minus 1 of Ik and R K minus 1 Kj. So what you will going to return from this, all these things you are going to return. So the return R of n means last matrix which we have taken. So we have taken the first matrix, that is called as the matrix of A, which we have taken already previously, and then we get it the last matrix, that is 1 1 1 and then 0 0 0 1 1 1, that is transitive closure. So we converted the matrix A into the transitive closure. That is called as, this is called as the Warshall algorithm. So time efficiency for this is nothing but the theta and q. Okay, so the efficiency for this specific efficiency matrices can be written over their predecessors. Matrices can be written over their predecessors with the space efficiency. Thank you.